Hello everyone. Hopefully my mic is working this time. Today I will help you understand one of the most difficult units of AP statistics in my opinion, simply because of how much memorization and how much different ways that you can do it, but I'm going to try to simplify it down so that you guys could understand this pretty well. I'm talking about all the four steps and all the different inferences that you can make from it. And from my personal experience in the AP test, this is not very covered too much on it, but it is very important to understand as uh, it is covered in at least one of the FRQs, and the FRQ takes up 50% of your total grade. Yeah, hopefully this video helps you. Leave comments below if you have any questions. I will be more than happy to answer. But to start off, I feel like it's very important to build the foundation, which is knowing the difference between a statistic and a parameter. Now, a statistic is something that you gain from a sample, whereas a parameter is a estimate. So we use statistics to estimate parameters. So an example of this would be like a rainforest has a parameter, a mean of 60 liters of rain every year. I don't know if that's true or not, but like, let's just say that, you know? So it's estimated, right? So that would be the parameter, whereas the statistic is um, what an actual sample is. So let's say we did an experiment or we observed this study, right? We observed this rainforest and we realized, oh, it got 58 liters of rain or water. That doesn't necessarily mean it's wrong. It just means it doesn't quite line up with the parameter. And that's what all the four steps are used to do. And it's to check, it's to check if something is true or false. Now, one very important thing that we have to keep in mind while doing four steps is that we never fully accept our null hypothesis. We either reject or fail to reject. And actually, I need to add an extra. Here, I'm actually going to make that right now. Type 1 error. Actually, I don't even need a visual for it. But um, we either reject it or we fail to reject it, and we never accept no matter what. So now we'll go into the different types of significant tests that there are in statistics. So I like to think of them as there's three main tests, three main different like types of tests, which are Ztests, Ttest, and chi-square, different chi-square tests. And for Z-tests and T-tests, there are a one-way and a two-way for both of them. And you can also get confidence intervals for both of them. And that's a different thing in statistics, and I will go over that in a little bit. The chi-square tests, there are two different tests that, or I guess there's three, but there's chi-square homogeneity, chi-square independence, and chi-square goodness of fit. And yeah, so what is the difference between the Z-test, T-test, and chi-square? So Z-tests, typically, you either know the standard deviation and if the normal distribution is above 30. So there are 30 samples collected, and there has to be more than 30 that fits the normal condition. And that's what separates the Z-test from the T-test, which are very similar, but the T-test is different because the curve that you're doing the test on is not necessarily fully normal. And as you can see, I'm not going to search anything on this computer. T curve, the T curve. Oh, that is very okay. The T curve, the Z distribution and the T distribution are very different. And as t gets closer to 30, so as the n increases, it gets closer to the z distribution. And to a certain point, you can basically, like, it's very similar to the z-test to a certain point. But it is important to know that it's different and it will give you different results, you know? So that's that. So what you can do is you can see what variables they give you to distinguish which type of test you can do. So if they only give you, going back to this, the statistic, right, and they don't give you any parameters of any kind, and it's below 30, then you know that you have to use a t-test, because you don't really have the means to test it through z. So let's go over z-test to start off, right? So you know that there are more than 30 people participating, and you know that the standard deviation is known. So what you can do, right, is that you have to make a four-step sheet for the exam, right? And you probably have already done this in class if you're watching this video. And yeah. So I'm going to be writing out all of these things. So the 4 steps to do a z-test. Now, during the exam, you're not really going to get the equations for it, but they do give you these 2 sheets, which will provide you with enough information so that you will be able to do the z-test. So let's do a z-test real quick. So for the state, you need the population. I want to just say pop. Sorry if my handwriting's bad. I'm trying to do this with a mouse right now. The parameter, the null hypothesis, the null hypothesis and the null alternative, or the hypothesis alternative, and alpha. In any given situation, the alpha is 0.05 unless stated otherwise. So this 0.05 is a test for significance. And we also learned in AP Psychology, in an experiment, if there is less than 0.05 difference, then it could all be up to luck, so we would reject, right? So the null hypothesis, it depends on whether you're doing a population proportion or if you're doing a mean. And in this situation, I am going to do a mean. So I'm going to do a mean z-test for population. This is just an example. Doing the z and t tests are practically the same. I'll show you the difference between them, but you just need to make sure that you're using the right formulas for each. So instead of this, I'm going to actually walk you through this sheet. So if you have one population and you know it's a z-test because it gives you the parameter, then you know you're using a z-test, and this is how you find the standard deviation and the standard error, which will give you the information for you to do the test statistic. So statistic minus parameter over standard error of the statistic, right? So and then for 2 populations, you basically do the same thing. You get the parameters, right? You get these 2 parameters, and then you are able to get the standard error of the statistic. And yeah. And for t-test, this is for one population. Remember, you don't have your parameter in this. You only have a statistic. So you're using different equations to get the different variables so that you can plug it into these equations. So let me just make up a scenario. Like, All right, let's go back to the rainwater, the rainwater scenario, right? So the population is rain water collected. This is terrible. I'm terrible at writing. The parameter is mean rain water collected. The null hypothesis is that the mean equals 60 because we know what it is, right? We know the parameter. Now, the alternative hypothesis, let's say we're testing if the mean is greater than 60, right? So this is what we're testing, and this is what we're given. So for the next step, we should state the test, but you don't necessarily have to do that. The reason being is that if you don't really know what test it's called, then you can just put the equation for the do part, and that will give you points for the AP exam. But for this, we would know it is the Ztest for population mean. Next up, we have to check if it is unbiased. So another way to say it is if it is random. Now, there are multiple different ways that you can mess up this parameter or condition, and that is if you're taking a convenience sample, there's word bias. That's why I like to think of it as like a bias. But if you get a simple random sample with no wording bias, then you should be good. And it's a random sample of a forest. That is a part of the problem. So this condition is met. And for any condition that is not met, basically what you can say is that you should proceed with caution. And yeah, but I don't think the test will necessarily throw you any of those curveballs. They might just proceed with caution, right? Now, is the sample independent? Independence is very important because this is like what separates, like, if I influence another study or participant, then that would make the study not valid. So independence is the size of the population, and let's say we sampled 30 trees, yes, 30 forests, right? We sampled 30 forests, and we have to multiply that by 10 because of this rule that I forgot the name of. But if there are more than this, what this number equals, then the independence is met. And are there more than 300 rainforests? Probably in the world. That's my paper. That's on this. Sorry. Is there more than 300 rainforests in the world? Probably. So the independence sample is met. So we could just give that a check. And then the sampling distribution, if it's normal. Now this is the big part that differentiates Z procedures and T procedures. And I'm going to go through every condition for each thing. All right. So for population proportion, your n times p hat, which is the percentage of the parameter, has to be greater than or equal to 10, and your n1 minus p hat should also be equal to or greater than 10. For population mean, your Z procedure has for a population mean, your number that you're sampling has to be greater than 30 for the central limit theorem to apply. If the condition is not met, then you have to proceed with caution. For T procedures, if the number sampled is less than 50, the sample must look normal. That means there can't be any outliers or it can't be skewed. If it is in between 15 and 30, the sample must be absent of outliers or strong skewness. So, yeah. And then if it is greater than 30, even if it's skewed, even if there are outliers, you are able to proceed because it is normal. It's fine. Because central limit theorem, I'm guessing. If this condition does not apply, then you have to proceed with caution and you have to write that down all the way. But let's test normality for my example, and normality is met because 30 is greater than or equal to 30, so that's good. Now comes the hardest part, which is the do. And this is the part, so up to this point, whether you're doing a confidence interval or a z-test, this should be the same, roughly the same, other than you can't state the null hypothesis or null or alternative hypothesis or an alpha up to this point, because they will take points off for that. But instead, you would want to say confidence or 95% confidence interval, which is usually what they do, or a something confidence interval. For this, what you got to do is, let's look at this. It's statistic minus, we're doing a z-test, so statistic minus parameter over standard error of the statistic. So we know the statistic of it is 58 in my previous example minus 60 all over the standard error of the statistic, which is p hat minus p hat 1 over n. So square root of hold up. Yeah. The standard error of the statistic, which is, I don't have a calculator on me, but you basically use this equation sheet and then you can solve that out, and that gives you a z-score, and basically you use this z-score to find the percentage or your p-value. A thing to note when you're finding your z-score, I don't want to delete all this, shoot. A thing to know when you're finding your z-score is that for z-scores at least, you're always going to be to the left of the graph. That means if you're trying to find all values greater than that specific number, then this is just the standard deviation, which I don't have because I made up this problem over the square root of 30. Where was I? Yeah, it's to the left of it, so anything less than. So if you want anything greater than that, then you would have to do 1 minus that number. Now, you should usually know when to do the 1 minus, as the p-value usually isn't that big of a number. If the p-value is 0.8, then I think you should probably subtract 1 and it should be 0.2, because they're trying to make the test tricky and yada yada yada. If you are doing a hypothesis where you're checking for inequality, so if it's not equal to, you have to multiply the test statistic or the z-score, the p-value that you get by 2, because you need to find both sides of this graph, if that makes sense. So let's just say the p-value equals oh wait, hold up, let me get this sheet. Hold up, let me just make up a p-value so we can all find it. Table B, is it table B? It is table B. Okay, so wait, is it table? It's table A. It's table A. I'm stupid. Alright. So table A is for z-scores and z's. So let's just say it was negative 2.9. Or crap. Let's just say it is, what's the other side? .9972. So let's say that the z value, so the probability that the z is greater than 1.9 equals 1 minus 0.9713. And if you pull up the calculator, 1 minus 0.9713, you get 0.0287. Now, the p value is 0.0287. Now, what you can do with this is you can see if this is greater than or less than the alpha value given, and because this is less than the alpha value given, we reject it, because an easy way to think about it is that if the probability is above the alpha value, then it's left up to chance. It could have been pure chance that this could happen, but because it's less than the alpha value, then you know for a fact that this hypothesis, or the null hypothesis, is rejected, and we accept, not really accept, but yeah, we reject h sub 0. So now for the conclude, you have to write down basically these words exactly. Because the p-value of, in this case, 0.028 is below the alpha value of 0.05, we reject h sub 0, which is that the mean is equal to 60. There is sufficient enough evidence to suggest the true, and then you put the parameter of interest, the true mean rainwater collected for rainforest water collected is greater than 60. I messed up. I'll admit I messed up. This is not supposed to be 58 minus 60. Why would it give you a positive p-value? If this was higher, it would have given me a p-value of that. But you guys understand the point. For confidence interval, you would be using this equation, right? This equation. You know your statistic. You know your standard error from last time, right? Now all you need to know is the critical value. Now, how do you find the critical value, you may ask? Well, it is found by the percentage of confidence that you would want. So you would need table B, not table N, sheesh, table B, and table B gives you the confidence intervals. So what is this? AP statistics. Oh, there we go. If only this would give me a better quality. Copy image. Paste. Sheesh. Oh, I didn't think this through. Why is none of it giving me? All right. Here, I will just use this just to demonstrate. On the very bottom of the sheet, it gives you the percentage, and as I stated before, the more n values that there is, the closer it gets to normal, to infinity, where it is basically normal. Now you find the confidence value by locating which confidence interval you want it to be in, and then you find it, and then you go up one to the infinity. And for the most used one, which is 95% confidence interval, it is a 1.96. And you use statistic plus or minus the critical value times that number that you just found times the standard error of the statistic. That's how you get your confidence interval. And the wording for confidence intervals is with this certain with whatever percent confidence. We'll just say 95% confidence. We believe the true, like stated before, the parameter of interest, which is mean rainwater collected for rainforest water rain, is between the lower value and the higher value. Now for T procedures, you need to find the degrees of freedom in order to find your confidence interval. Now, your degrees of freedom for your T interval, or for your T. Oh, why am I making a cow? Christ. I'm just selecting, trying to delete stuff. So let's say you have a population of 20 or 33. Their degrees of freedom is the n minus 1. So this 33 would be a 32. Now, in table B, you go to the left, and then you find your confidence interval. You find your degrees of freedom here, and then you go over till the confidence interval. Now, this doesn't cover all the values, but what you need to remember is that you always round down. So let's say it is, let's say there are 80 people. Your degrees of freedom would be 79, but because in table B it goes from 30, 40, 50, 60 straight to 80, you would use the lowest value. So you would use 60, and let's say you're using a confidence interval of 95. You basically go to the intersecting point, and your critical value is 2. I think. Yes, it is 2. So that is Z and T confidence intervals covered. When you're using 2 samples, when you're using 2 different things, you always subtract, and you're usually subtracting the difference between 2 means. And you can use this sheet. So if you're using 2 populations, or if you're doing a Ztest, this is how you would do it. So this gives you the standard error, this gives you the parameters, this gives you the standard error, this gives you the parameters. That's how you do it for 2 populations. Same way, and that covers 2 out of the 3 main statistics. The last one is a little bit more complicated, and that's because it's chi. So chi-squared is the idea that there are many different samples, and it is a easier way to basically solve for them. So let's say we're testing dice rolls, and we're seeing if this dice is actually legit. You because there is only one variable, which is the number rolled. You would use chi-square goodness of fit, and basically you would roll out all your values. You would put them on a table, and then yeah. Now, many things of chi-square are usually the same, except for normality, and that is because chi-square is a little bit different from that. Give me a second. I'm talking for a really long time. Where's my chi-square sheet? Oh, there it is. So you need to see, so conditions, it needs to be still unbiased, so random samples, no convenient samples, and it still needs to be independent, which the size of each population has to be greater than 10n. So yeah, otherwise proceed with caution. Now the big difference is that you need to find out that the expected counts are at least 5. So in this dice roll scenario for this goodness of fit, we need to, if let's say I only did 10 tests, 10 times 1/6, which is the probability, does not equal, or is not greater than 10. So the number of dice rolls you would need would be at least 60 times 1/6, so that all the expected values are greater than 10, or are greater than 10. So this condition is met here, but not up here. Does that make sense? I feel like I'm rambling, but hopefully everything makes sense. Yeah. So how do you find expected values? It should give you a percentage of each thing, and it gives you the population, and that's how you get the expected count. Or no, not 10. It has to be greater than 5. Sorry, my apologies. 5. 5 is that magical number for chi-square. So the probability of a coin flip, I mean, I guess you really wouldn't use a coin flip, but it's 1/2. So let's say you do it 60 times. The expected count would be 30 and 30. What about, I don't know. What about, like I said, the dice roll, so it's 1/6. But not always is it the same. It could be like M&M's, so it could be like a 12% red, 33% blue. You just multiply that by the population, and that's how you get your expected counts. That's how you get your matrix. Now, the chi-square, now that is just goodness of fit. If there are more than 2 variables, or if there are 2 variables, then it's independence. And if there are more than two or more sample groups, all right, wait, hold up, back up. If there is one sample group but more than 2 variables, then you do chi-square independence. And if there are 2 or more samples groups, then you do homogeneity. And the difference between independence and homogeneity is very, very slim, as it is basically just the wording for the conclude. So there is a very easy way to distinguish them. I don't have my shoot. There's a very easy way to get the expected count and basically do the whole test, and that is basically the way that you should do it. If you want me to make another video to show you how to do it by hand, drop a comment down below or let me know. But basically what you do is you go into your calculator, you type in whatever word that represents your sample. So I'm going to just do cars, right? And then you do equals, right? You do control equals, and then you want to make a bracket with how many rows of whatever you want. So cars equals, and then you type in your values that is either given you by the table or you have to find them yourself. Usually 99% of the time it's given to you, so you got 10, 12, 13, 1, 3, 4, 6. I'm just putting random stuff down. 14, 18. And then after you set that equal to each other, you go to your menus, you go to statistics, you go to stat tests, and then you do chi-square, two-way chi-square test, and then you basically click that. You go to cars, or you have to enter cars first. So you set this distribution equal to that, and then after that, it should give you a bunch of values. It should just give you your p-value, which is basically the do. But what you need to do is you need to go to var, and then you need to go comp expected values, and that's what's going to give you the expected value matrix of that you're going to test it with. So basically it's all in the calculator. I don't have a calculator app on my device right now, on my computer right now, so I can't really show you, but it's all in your calculator, and then you just check if each of those values are greater than 5, and make sure you write down each chi-square. An example of this is the AP Statistics project that me and my friend Ttest worked on, where we were testing independence between consistent sleep and gender. So we had, these are our two distributions. This is our observed count, and basically I put this into my calculator, I put the matrix for these 4 values in, and I was able to receive the expected count. Because all of these are greater than 5, greater than or equal to 5, I was able to continue. If not, proceed with caution. But this is the plan. The sample is random, it is independent, and all expected counts are greater than 5, therefore a normal condition is met. And then for the do, it gives you the chi-square, which is that, and the degrees of freedom is the number of rows minus 1 times the other number. Oh shoot, I didn't mean to remove that. Oh crap. Times the other number of rows times 1, or minus 1. So let's say for this example, there's 3 rows, so it would be 3 minus 1, and then multiplied by the 3 minus 1, and it would be 2 times 2, which equals 4. That's your degrees of freedom. Our p-value is 0.05, and we concluded because the p-value is below the alpha of 0.05, we reject h of 0. There's sufficient enough evidence to suggest that gender and consistent sleep schedules are not independent. And yeah, that should be everything that you should need to know about inferences and 4 steps. But the very last thing that I want to touch on are type 1 and type 2 errors. Now, one of them is rejecting when you shouldn't have, and one of them is failing to reject when you should have rejected. Now, I personally struggled a lot with how to memorize it, but then there is a very simple trick in how you could memorize this. So if you think about a pregnancy test, right? If you get 1 line, right, that means that you are not pregnant. But if this is wrong, which is these are errors, so these are wrong, one line means that you rejected when you should have failed to reject. And then type 2 errors is, or yeah, and then type 2 error is failing to reject when you should have rejected. So this is a false negative or false positive, whereas type 1 is a false negative. I don't know if that trick helps you. Personally, it did help me a lot. But yeah, false positive, false negative. Just think of pregnancy tests. You should be good for the AP exam. And I think that wraps up my video. I don't know what much more I can cover. Oh, yes, chi-square. The distribution is skewed, and it always goes to the left. The good thing is you're always testing it goes to the right. The good thing is you're always testing to the right. The probability is you're always testing the probability to the right. Yeah. Hopefully this video didn't put you guys to sleep. Yeah. Oh, also the more degrees of freedom that you have, I think the more normal it gets. So, yeah. Hee. Very good, everyone. I hope you enjoyed. I hope this might have helped. I kind of felt like I was just rambling for literally forever. I really hope nothing gets corrupted. I really hope my microphone didn't not work. I don't know why I'm still talking. Good luck on the exam if you're taking it. Thank you guys for watching.